Okay, so this video talks about finite fields and then what happens with the Cartesian planes over a finite field. And I'm not going to do tons and tons of examples of finite fields, mainly because we're actually mainly going to focus on infinite fields for this course. So, to remind ourselves what a field is simply some set. It's going to have two operations, addition and multiplication, where the set has to be closed under addition and multiplication. It also has to be an abelian group with respect to addition, an abelian group with respect to multiplication, with the caveat here you throw out the zero element. Okay. And what does that mean? It means it doesn't matter how you add or multiply elements together. You can also add and multiply together at the same time. No worries, you can do whatever you want in terms of adding and multiplying elements together. You also have to have a zero element and inverses for all of your elements. You also have to have a one element and inverses for all of your non-zero elements. Okay, so that's the reminder of what a field is. So we've looked so far at, or I guess I should say, if you've watched the previous video, we've looked at infinite fields. So now let's look at finite fields, because you could actually do that other video after this one if you want to. So that's the idea behind a field. So finite fields. So here are a couple of examples. So the first example of a finite field is simply somebody called z mod 2. Okay, so z mod 2 is, in terms of elements, simply the elements 0 and 1. This is the smallest field you can ever have. Why? Because if you go back to the definition of a field, notice what you have to have. It straight up tells you in 1c and 2c you have to have a 0 element and you have to have a 1 element. And here's the key thing that I didn't really stress, they can't be the same element. So that means bare minimum you have to have a 0 and a 1 element. Z mod 2, only the 0 and the 1 element. Okay. Now, you also have to define how addition and multiplication works. So here's what we're going to say. We're going to say add them like normal, multiply them like normal. Except that's not going to work. So we are going to define addition as addition mod 2. And at this point, you should already know what mods are. If not, here's the crash course. For mod 2, what it says is if you get an even answer, call it 0. If you get an odd answer, call it 1. Now, that's totally layman's way of describing mods. Mods, really, in this connotation, are going to be you want the remainder after you've divided by whatever the mod number is. So here, if you divide by 2, your remainder is either going to be 0 or 1. Okay. So here's what you do if you can add all possibilities of 0 and 1 together. You would get this little chart right here. So you could add 0 plus 0. Well, 0 plus 0 is, don't overthink it, still 0. 0 plus 1 is still 1. 1 plus 0 is still 1. And the only one that's slightly interesting is this guy right here, which is that guy. So 1 plus 1 is 2. Wow, that's a terrible equal sign. Let's pretend I didn't do that. Okay. Now 2. Divide 2 by 2. The remainder is, well, 0. So this guy would be the same as 0 mod 2. Okay. So that's how you would deal with that guy. And that's why we put the 0 right there. Notice what this tells you with this chart, or this addition table. This is a technical term. This tells you automatically that what? It tells you that you're closed under addition because you got only ones and zeros inside the table. It also tells you that you are commutative. In other words, the order in which you add doesn't matter. You can tell that by, you look down the diagonal, and if that guy was a matrix, it would be a symmetric matrix. No, it's not a matrix. But notice, it doesn't matter if you add 1 to 0 or 0 to 1, you got the same result here. Okay. If we then, and you can also use the table to show that this is also the associative property. You can also use the table to show that the 0 element in this particular case is just going to be the number 0. And you can also go ahead and find all of your negatives as well. The negative of 0 is, well, still 0. And the negative of 1 is, well, still 1. Okay. Now, if you go and look at the multiplication table, you can do the exact same thing. Here, what happens? 0 times 0 is 0. 0 times 1 is 0. 1 times 0 is 0, and 1 times 1 is 1. And notice we actually, for multiplication, you didn't even have to do that if you didn't want to. Okay? They all multiplied together very nicely. Now notice what this tells you. This tells you that your one element for this field is simply that 1. And it also, if you wanted to, you could totally go and find all of your inverses. Now remember, the 0 element doesn't have an inverse, so that means we're only looking for the 1 element, and 1 times what equals 1? Don't overthink it. The inverse of 1 is still 1. Okay? Actually, here you didn't want to put the negative there, so I'm going to put the little plus sign right there. Okay? So that would be what we just did there, showed that, hey, this particular set is in fact a field. Now, once you've established that you've got a field, we can start looking at other things. And the big thing that we look at with fields is we look to see what their characteristic is. So pause the video right now, see if you can't grab your characteristic. Remember, the characteristic of a field is simply what? It's the number of times you add 1 together to get the 0 element. So take a pause here, I'll count to 5 and I'll start up again. And when you got your guess, restart up the video. Alright, so turns out you do the following. So we know that our identity element, or our 1 element, is the same as 1. So we add 1 and 1 together, we get 2, except addition is mod 2. So we know that 1 plus 1 is really 0. So we're going to go ahead and switch that 2 to a 0. Why? Because we were doing addition mod 2 right here. Now, what did you need for characteristic? You wanted to know the number of times you add 1 together to get 0. In this case, your characteristic would be exactly 2. Okay? And that's it. That's all you got to do. So that's it for that example. So let's check out one more example. Suppose you have z mod 3. So z mod 3 is done the exact same way. You've got the elements 0, 1, and 2 now. So 3 elements. A z mod, fill in the appropriate subscript. So z mod n, you start with 0 and you walk up all the integers up to 1 less than whatever the subscript is. Or if you prefer, the subscript tells you how many elements are in the set. In terms of addition and multiplication, it'll be mod 3. Why? Because if you take the remainder of any number after you divide it by 3, the remainders are going to be 0, 1, or 2. This is why we do mods here. It's also why it's red z mod 3. Okay? So, just like with the last example, we can totally put together the addition and multiplication table. They definitely take a little bit more effort here. In terms of adding, 0 plus anything is the anything. So that actually tells you your 0 element, and I'm going to be lazy and just put an F here, is just that 0. And notice 1 plus 0 is 1, 1 plus 2 is 2, 1 plus 2 is, well, 1 plus 2 is really 3, but 3, when you divide it by 3, has a remainder of 0, so that's the same as 0 right here. Okay. Notice same thing happens when you have 2 plus 1, that gives you back 3, so you still get that same 0. And this one right here is 2 plus 2. Well, 2 plus 2 is 4, but if you divide 3 into 4, you get a remainder of 1, so that's why you would get the 1 right here. Okay. It's pretty common. I shouldn't say pretty common. If you put your table together correctly for a z mod n, you're going to get with the addition table something that looks like this, where the first roughly half of the numbers you just add up like normal, and then when you deal with the mod, it's going to be that roughly half again. It's not exactly half because you've got this stripe right there. Okay. Now, this table tells you a couple things. It does tell you can add your numbers together in any order that you want to. It tells you that you are commutative in your property. Notice here, how about 1 plus 2 is 0, 2 plus 1 is 0. In other words, this guy is symmetric if you look at it like a matrix. Okay. We can do the same thing with multiplication. If we look over here at multiplication, 0 times anything is 0. 1 times anything is, well, the anything. So that tells you that the identity element is your 1. Okay. And then the only thing that actually takes a little bit of calculation over here is this last guy, and that is 2 times 2. In other words, 4. and 4, when you divide it by 3, has a remainder of 1. Okay. With multiplication, always the first two rows and columns. The first row and column will be 0, second row and column, assuming again that you ordered it in ascending order, will just be a copy of the outside bits. So you only start getting anything interesting once you hit third row through third column and beyond. Okay. This one here, multiplication, you can multiply it in any order you want. You can see it from the chart here that, again, this guy is symmetric. You can also notice that the way we define multiplication and addition is what you start off and do normal integer multiplication, division, and then you mod out. So think about what works in integer, addition, and multiplication. Integers, the only issues that we had with integers not being a field was the fact that their inverses didn't exist. So let's go ahead and look at inverses here, and we'll deal with both the negatives and what you would hope were reciprocals but aren't going to look like reciprocals. Okay. So over here with addition, we have our three elements, 0, 1, and 2. If we look at their negatives, this is going to be the thing, and remember here definition, a plus the negative of a is supposed to equal your 0 element. So 0 plus what equals 0? Well, 0. Here's the 0 you're looking for. So that tells you the negative of 0 is still 0. Don't overthink that one. Now if you look at 1, go into the chart, 1 equals 0 here. So read out of the chart, that tells you the negative of 1 is actually 2. Okay. And if you look at 2, go into where there's a 0 in the table. And the only way we got the 0 in the table was from that 1. So this tells you that negative 2 equals 1. The other way to do this is just subtract 3 from the 1 and the 2. That's the shortcut way. Subtract 3 from those two guys. Why 3? Because you're z mod 3. Now if you want to deal with inverses, they're all supposed to exist as well. Except for 0, 0 never exists. Fun fact, the inverse of 1 is always 1. So let's check it out. What's the definition of an inverse? A times its inverse is supposed to equal 1. So if we look at 1, we go into where we find the 1 in the actual table, and notice that only happened when you multiplied 1 by 1. Okay. Now if we look for the inverse of 2, we're going to go into the table from 2. We got a product of 1 and we go out, and that tells us 2. So this tells us that the inverse of 2 is exactly this in this field, the same as the number 2. Okay. Now, we've actually talked about this a little bit in the past when we had that previous example a while back ago when we had mod 5. This is that same arithmetic, only not specific to mod 5, a little bit more in depth. Okay. So what that tells you is all your inverses exist, all your negatives exist, your 0 exists, your 1 exists, you can add and multiply in any sort of way that you want to. This guy is another example of a finite field. Okay. Now, what do we want to do with all of this information? We want to look at what the characteristic of this field is. Okay. So if we look at the characteristic of z mod 3, we want to know how many times can you add 1 together to get a 0. Well, pause it for a sec, think how many times you can add 1 together. And we'll be back in just a sec. Okay, at this point, I'm going to assume you've already paused the video. You've checked out what you think your guess for your characteristic is for z mod 3. So here is a way to do it. If you have 1 copy of 1, obviously that still equals 1. If you add 2 1s together, that equals 2. And 2 is actually a number in our set, so that's fine. And if you add 3 copies of 1 together, well, that's 3, except, whoa, we can't have 3. 3 is really the same as 0 in our set. So what does that tell us? That tells us, hey, we have what? Well, we have characteristic 3, because we added 3 1s together. Okay. And that's it. That's your finite fields. Now, do we in and of it themselves care about finite fields? Nope, we care about geometry in this class. And everything we've done so far with finite fields is totally like a modern algebra and abstract algebra topic, okay? Or I guess number theory, you can do things in there too. But anyway, we care about throwing this into some sort of geometry, so we're going to look now at Cartesian planes built from finite fields. Now, if you haven't looked yet at what a Cartesian plane is, this is where you need to stop this video, go look at the previous video that gave the detailed definition of a field, which we actually went over again in this video, some examples of infinite fields, but it also at the end talks about what a Cartesian plane is. So, we're going to build our Cartesian plane over Z mod 2. Our points are going to be ordered pairs where the x and the y coordinate can only come from our field. So that means they can only be 1 or 0. Okay? Which tells you you have 4 possibilities. 0 or 1 in the first slot, 0 or 1 in the second slot. So you can have 0, 0, 1, 1, or both 0, 1, or 1, 0. Don't overthink it. Okay. Now, the next thing that we want to do is we're going to define our lines. And according to how we define Cartesian planes, our lines are of the form ax plus by plus c equals 0, where your a, b, and c, and this 0 at the end right there are all coming from your elements 0 and 1. Okay? Now, you might be thinking to yourself, hey, I've got 3 options there. I've got 3 options. I lie. Let me back up. I've got 2 options in this first position, 2 options in the second position, and 2 options in that third position. There should be 8 lines in this Cartesian plane. Nope, turns out that's not the case. Instead, remember our caveat. Our caveat is you can't have both A and B equaling 0 at the same time. Okay? So I'm going to claim that there's actually 6 lines. So I'm going to go ahead and build them up right here, and then we'll throw them in a list once we're done. So here are our options. You could have A equaling 1. Okay? So if A equals 1, if you wanted, you could have A equals 0. That's totally fine too. So if A equals 1, that means you're definitely going to have your x term. Now, what can happen next? Maybe you have B equals 0. Well, if B equals 0, right here, that means the y term disappears. So we'll say here, B equals 0 as well. Okay? So that would mean either C equals 1 or C equals 0. Okay? Then we could have the situation where B equals 1. And if B equals 1, you'd have x plus y. And maybe C still equals 1. Or you can have where C equals 0. Okay? Now, next case, A equals 0. If A equals 0, B can't be 0. So this is only when B equals 1. So what do we have? No x term, but we do have to have a y term. And you can either have C equals 1 or you can have C equals 0. Okay? Now, I'm going to rewrite these terms in a more convenient way. Okay? X equals 0, y equals 0, no worries, they're done. But if we look here at x equals 1, x equals 1 is actually, well, we can add 1 to both sides. If you add 1 to both sides, you'll get an equals 1 on the far side. But if you add 1 to 1, well, what happens? 1 plus 1 is 2, but remember, we're Z mod 2. 1 plus 1 is really 0 in this system. So we just get x equals 1. So if there is no y term, x equals either 1 or 0. Now I'm going to skip this middle guy. We'll come back to him. But if we look down here at when we only have a y term, we can do the same thing. We add 1 to both sides. So we'll get y equals 1. And here when we added the 1 to the plus 1, we'll get 1 plus 1, which is 2. 2 is even, so that's really the same as 0 in this field. Okay? So there's 4 of our lines. We still have 2 more. Now, for these next 2 lines, I'm going to go ahead and solve for y. So to solve for y, I'm going to add x to both sides. So this is y plus now 2x equals x. But remember, 2 is what? 2 is the same as, and let me write it down here. Recall, 1 plus 1 equals 2, which is the same as 0 mod 2. So this term of 2x is really gone because it's 0. So this is the same as the line y equals x. Okay. Now for this next one, I'm going to be a little bit sneaky because I'm going to keep a negative in it. And I'm only going to keep the negative in it to make our lives a little easier. So what I'm going to do is I'm going to add 1 to both sides. Well, if we add 1 to both sides, we'll have y plus x equals 1. Technically speaking, we can go ahead and either add x to both sides, and if we add x to both sides, we would get y equals x plus 1. But that's actually going to make our lives a little bit difficult when we try to put this in a picture format. So instead, I'm just going to subtract x from both sides. And remember, negative 1 was the same as positive 1 in mod 2 because the inverse or the negative of 1 was positive 1. Okay, so here are the the 6 guys that we're going to grab. X equals either 1 or 0, y equals 1 or 0, x equals y, and y equals negative x plus 1. Technically speaking, this last one's more proper, but this is the one I'm going to go ahead and use for us. Okay, so those are our 6 lines. Oh, awesome. I threw it in. I forgot I threw these in. Okay. So those are our 6 lines. Now, and this one here, remember that's the same one as y equals negative x plus 1. We just talked about that. Now let's put this in an actual picture format. Okay, so first thing is go ahead, I'm going to orient our 4 points in the standard orientation for an xy coordinate plane. We've got the origin 1, 1, 1, 0, so our unit points right here, and then 1, 1. So then we look at the lines. We've got y equals 1, y equals 0, so y equals 0, y equals 1. We have x equals 0, x equals 1, so x equals 0, x equals 1. Notice you can pull them totally off the coordinates of your points, or since I oriented these 4 points in the same way as a normal Cartesian plane or a real Cartesian plane, you just go ahead and graph what you know. Now, x equals y, that would be only those 2 points, or the same normal line that you would think. And y equals x plus 1, notice what this tells you. This tells you that your y coordinate is x plus 1, the x coordinate plus 1. It's going to be the line right here. Notice down here, if you add 1 to your x coordinate, you get 2, but 2 is the same as 0. So that's why this one would work. Or if you think of it as y equals negative x plus 1, you can think of it as this negative slope like we normally think of it. Okay, so that would be our finite geometry is what happens. If you have a Cartesian plane over a finite field, it turns out you're going to have a finite geometry. And this one here, if you look at the video that deals with proposition 14.1, one of the results says if you have a Cartesian plane over any field, you're going to get an affine plane. Notice this guy right here. This is our affine plane on 4 points that we had back with finite geometry. Now, what's one of the things that we know about finite geometries? Finite geometries don't satisfy all the betweenness axioms, which means they can never be Hilbert planes. We want to get to Cartesian planes that are also Hilbert planes. So in order to exclude these cases, sections 15, 16, in other words, the end of chapter 3, is going to have some extra criteria you have to put on your fields to make sure they're not going to be finite fields and make sure all of the betweenness and congruence axioms will hold. Okay, turns out to be nothing earth-shattering. It's exactly mimicking what we did when we were dealing with our 4 models or our models back when we were in chapter 2, but it is going to say, hey, finite fields, we really don't want to deal with you because you're not going to be Hilbert planes. Okay. Now, I don't have prepped up on slides, but I did want to go ahead and show you what the Cartesian plane over Z mod 3 looked like. Okay. That is this one. Okay. So if we look at the Cartesian plane over Z mod 3, it'll turn out to have a total of 9 points. Ordered pairs still, where both of the two x's and y's are going to come from z mod 3, so you can have 1 through 2 in each of the positions. Now, I didn't actually write them out here, but I did go ahead and graph them. So you've got the origin, then 1, 0, 2, 0, and then the appropriate points up here. Then we have the lines of the format ax plus by plus c equals 0, where a, b, and c are only the numbers 0, 1, or 2. And it turns out the easiest way to draw this picture is you go ahead and you graph all of these resulting lines. Okay? I'm not going to write out all these equations, but you totally could write out all the equations and you get the correct number of lines. Okay? So this here would be an example of what can happen when you start getting finite field that's larger than just z mod 2. Okay? Just as a heads up, if you are wanting to look at sort of the go-to in finite fields, they are z mod, and the number here in the subscript actually has to be a prime number. If you don't have a prime number in the subscript, it's not going to turn out to be a field. It'll be a perfectly fine set that acts exactly like z mod 2 and z mod 3, but you'll actually miss out some of your multiplicative inverses. They won't all be there. You actually get what are called zero divisors, and those are bad. Can't have them in fields. Okay, but we're not going to talk about zero divisors in this class. If you've had the modern algebra class, you may have heard about them already. If not, it is something that's out there. Okay, but that's it for finite fields, and then finite fields with Cartesian planes. There's lots more in this section, but that's it in terms of finite fields.